Good afternoon. Can everybody hear me and see the PowerPoint?
Yes, sir.
All right. Are there any questions?
Hello, Professor.
Yes.
By any chance, have you seen my email that 2 days ago after you sent out the email about grades being posted on Blackboard?
Yes.
Uh,
I will take these up after all of them have arrived tomorrow at 5 minutes to midnight.
yeah, because I don't have a grade on my exam.
All right. I will look at that. But as I said, that's why I gave everybody the deadline until tomorrow. 5 minutes to midnight, and so that's the cutoff point, and at that point we'll look into things. Okay?
Okay.
I will, don't worry, I will get to it. It just will be a little while. Any other questions?
Yes, Professor.
Yes.
So some of us couldn't make the meeting on the 31st, and I believe there you discussed question 1, where it was talking about proof. Wait, let me. It was the proof that's going to be coming up that we'll have to do on the next exam. And would you mind going back over that so that we can get it recorded?
But you just said that I already did it.
Well, yes, but a lot of students rely on the recordings, and it wasn't recorded that day by one of our students.
I'm sorry, this is what online synchronous class is all about. If you don't record, if you don't attend, then I'm not going to repeat things. I mean, I will quickly go through it, but I will certainly not go into any details. Which question are you looking at?
Looking at well, I'm looking at like a different thing. I don't have like the exercises right in front of me. But it's the one, let me see. Sorry, I have to pull it up. It would be like prove that the following language L is not context free, and then you have the language.
Yeah. What is the language?
Well, I can give this one as brackets A to the K, B to the J, A to the I, and I greater than J greater than K, all greater than or equal to 0.
I think that was I greater or equal to J and K. Equality, right?
I mean, I guess. I think I'm looking at a different problem, but I didn't download the exercises.
All right, so what you do is, in this case, you just take a word, for instance, a to the n, b to the n, c to a to the n, which is in the language for any n. So you pick n, the constant in the pumping lemma. And then you have, so this is your z, and the z is u, v, v, w, x, y, and vx are both epsilon. So v and x are at least together of length 1. And for all s greater or equal to 0, u v to the s, w x to the s, y is also in the language for all s. And so, because that's of course true, because z is long enough, n is the constant in the pumping lemma, so this is actually 3n in length. And so then you have to explore all possibilities for v and x. And so you can have v in the first a, in which case of a's, in which case s is equal to 0 is going to well, you have to be a little bit more careful. First, you have to assume, as I did last when I covered it, v is epsilon, and in that case, you have x somewhere, and so then the x has to be of length at least 1 if v is epsilon, and then you take s is equal to 0, and since the x can't be covering things from the, so you have this situation, you have a bunch of a's, you have a bunch of b's, you have a bunch of a's, and so if x is epsilon and s is 0, then the x can be in the first a or in the b or in the second a, or it can be straddling the boundary, but it can't be a and b and a, so s is equal to 0 is going to get you a contradiction. So if v then is in group 1, so call this G1, G2, G3, if v is in G1 and v is not epsilon, then you can simply say s is equal to 0, which reduces the number of a's, and then it will give you a contradiction. If v is in G1 and G2, so it's straddling somewhere here the boundary, so there's an A and a B, you can again take s is equal to, well, you can take s is equal to 2. That will give you A followed by B followed by A followed by B, and then again, so that is going to be a contradiction. If v is in G2, then you say s is equal to 2, which too many b's, and v in G2 and G3, then s is equal to 2 gives you again a contradiction by the same argument that you have b's followed by a's and too many changes, b followed by a. And finally, if v is in G3, then of course s is equal to v in G3. In that case, s you can make 2, which means you have too many a's. So in each of those cases, you get a contradiction, and because you get in each case a contradiction, you then have a contradiction to the assumption that the whole thing started with, namely that there is a context-free grammar that will generate this language, and therefore you now have a contradiction in every one of the cases that we've enumerated. So in this case, there are 1, 2, 3, 4, 5, 6 cases. All right, so does that give you a little bit of an idea?
Yeah, it certainly does.
Okay. Any other questions?
I have two questions. One of them is a follow-up question for this. Do we, I know that you mentioned at one point that we have to explore every path possible. Whenever we're proving, are we supposed to find every single contradiction, or finding one contradiction is enough to prove it
For
wrong?
every case, you need one contradiction.
Okay, so just one of these contradictions on its own would actually be enough to break.
It will invalidate that particular case. Now, if there are other cases that you didn't consider, then of course that is going to be a hole in your argumentation. But if you, the argument is it has to be true for all S. Okay, that's the statement of the pumping lemma. And because it has to be true for all S, if you find one S where things get screwed up, then that is good enough.
All right, thank you. Now I have my next question is, I was working on part 2 on the exercise set 3, and I kept on,
Question
so,
2?
yes, question 2, exercise set 3. And I kept on finding, whenever I was looking for extra resources, this left stack and right stack information. I don't think we've actually gone over left stack or right stack. I just wanted to make sure that was part of, for example, I saw it for 2A. And
Okay, if you look at the stack, now if you write the stack this way, then there is no question. Now, the problem is when you do the stack in the way you write. So in the table you have a Q and you have an X, and then you have say an A, and so that gives you a P and a ZX, for instance. Now what that means is, in this case, we're tilting this that away. So this is now that way, which means if this is the X, then this is the X, and this is then the Z that we put on top of the stack. So we put that Z there. So the stack then grows that away. You can do it, you can tilt that stack the other way, and so it would grow this way, but that makes it more complicated, and so we're not going to do that. Okay?
So, for example, 2A, is there a way that you can just set up the, how
2A.
2A is the, where it says
2A is, I've talked about that at least twice. All you have to do is do the first half, which we've done. Bunch of A's, zeros followed by 1, same number of ones. And so you do that, and then you do the second half, bunch of A's followed by zeros followed by twice the number of ones. And then you have a new initial state that under epsilon is going to go to Q1, if that's your initial, well, call it Q01, so it's clear, and Z01, which is for Q01, and Z01 are for 0 to the I, 1 to the I greater or equal to 0. And then we have Q02 and Z02 for the other one, 0 to the I, 1 to the 2 to the I greater or equal to 0. And so you go non-deterministically to Q02 and Z02. And so in this case, everything else is nothing. And so in this case, you basically start either this push-down automaton for that language, or you start this push-down automaton for that language. And since it is either one of them, it forms the union, and that takes care of both of them.
I see. All right. So that one has nothing to do with the stack itself in terms of left or top down.
Absolutely not.
Okay,
You could
so
do either one of either. You could do this direction, or you could do that direction. As long as your two automata do the same direction, it is fine. But we're using this one.
mm-hmm.
The reason why we're doing it is because that's the way it makes it easier for the going from Greibach normal form to a push-down automaton. That basically assumes you're building the stack that way, because when you do a leftmost derivation, then you have a WA and gamma, and then you have W little a something alpha and gamma, alpha, where A goes to A alpha is a production, and so in that case you're basically building it up that way. Okay?
Yes, sir. Thank you.
Any other questions?
On the first slide, you have V in G1 and S equals 0. Could you explain how that
Which
is
one?
invalid?
V and G1 and S.
Because the A to K is less than B. So when S is 0,
Oh,
just
I'm
removes
sorry,
one
I did that backwards. You're absolutely right. I don't remember. So in that case, no, you're absolutely right.
Okay,
You
I thought
do
I was
S is equal
misunderstanding
to,
something.
no, you do S is equal to 2. Now this, okay, let me, I actually assumed that the first group of A's is greater or equal to the second group, but it's actually is smaller or equal. So let me double check that. I'm sorry. So we have to change that to S is equal to 2. That basically increases the number of A's here, and so that screws things up because we started with that. And then this is, of course, always okay because of the inversion. V in G2, if we take S is equal to 2, then let's see, we're going to make more B's than A's. So this can be smaller than that. So in that case, we take S is equal to 0. I'm sorry, this inversion is fine. S is equal to 0. That still, so the argument then is a little different, more. So in that case, we eliminate at least one B, which means we have fewer B's than A to the N in group 1. Okay, group 1, of course, still has N A's, and so if we make that S is equal to 0 when V is in G2, then obviously that's going to screw things up here. Because now we have more A's, at least one more A in the first group than in the B's. And then that is, of course, still okay. And if V is in G3, then, okay, in that case, we take S is equal to 0. Sorry, too many A's in group 1, because we eliminated at least one A in that third group if V is in G3. And so that means the leading A's should be no larger than the trailing A's, but since we killed off at least one A in G3, it means there are now fewer A's here than there, at least one. So this still has N A's in G1, and the resulting thing then has at least one A less, and so that will then screw things up. Sorry about that. Okay?
Thank you.
Okay. Any other questions? All right, so let's look at Turing machines. Turing machines is the last type of automaton that we're going to look at, and it is the most powerful device we have. It is not particularly efficient, but it can do anything that you can do. Now, this is, of course, a claim that is basically not provable, because one would have to have a concept of what one cannot do, and by and large it is the usual story that it is very difficult to deal with a negative. I've racked my brain, and basically I can come up with something that can be described but not done. But this is sort of a little bit out in left field. If you're asked, how do you get to a particular place, and you say you take this road, which is a one-way street, and you go on that road, and 1 mile before the railroad tracks you turn left. Now, this is obviously a description that could very well be valid, but it is not something that you can do, at least not legally, because if you're on that one-way street and you are supposed to turn to the left 1 mile before the railroad tracks, well, how do you know? So once you hit the railroad tracks, then you know I should have turned 1 mile ago, but you can't do that anymore because it's a one-way street. So this is, as I said, somewhat contrived, but that's about the only thing that I can come up with that you can describe, but you cannot do. But for the most part, if you can do something, then in some way you can formulate it as an application of a Turing machine. Now, there is, of course, the question of defining a language versus generating something. You can use Turing machines to generate languages, but for the most part, we are basically using Turing machines to define languages, in the sense that we test whether a word is in the language if and only if the Turing machine. Accepts W. So that defines L. What do I mean by in writing down? You can, of course, enumerate all languages in L. So if L is W1, W2, W3, and so on, you could, in fact, have a Turing machine that generates W1 followed by a marker, then follows W2 followed by a marker, and so on and so forth. So in a way, the test whether something is in a language is not really that significantly different from enumerating all the words in the language, but basically we're just going to look at this issue and not concern ourselves with the enumeration of all the words in a particular language. It should, of course, be obvious that if you did that enumeration game, then that Turing machine clearly is not going to stop if the language that is involved is infinite, because there would always be another word that could be generated and would be appended to that enumeration of the words so far. But basically we're going to look at this primarily. And so the question then is, what is a Turing machine? And as I said, you have essentially a tape that consists of cells. Each cell contains a letter. And you have, for all practical purposes, a finite automaton that has states and changes from one state to the next one. And then you have a read-write head, which looks at a particular cell, determines what is the content of that cell, determines what the finite automaton is in, what state it is in, and then on the basis of the state and the content of the cell that the read-write head looks at this point, then changes the state to another state, changes the content of that cell that the read-write head looks at, and moves either to the left or to the right of that cell. And that is one move. So what that means then is that a Turing machine, M, is a group of things consisting of a set of states, finite set of states, finite set of states, and a alphabet of input symbols. T is alphabet of input symbols. And then we have a T0, which is the alphabet of tape symbols. Obviously, T is contained in T0. Every input symbol, presumably, has to be viewed also as a tape symbol. But we also have an additional tape symbol that is the blank. And the idea basically is the following. Your initial situation, and I will continue with that, but the idea is that initially your tape contains your input with the read-write head looking at the first letter of the input. This is, of course, now an input that is over the alphabet of input symbols. So the input is a string in T star. And as I said, the read-write head initially is going to look at the first cell of the input. And everything else in that tape, and that tape is basically semi-infinite. It starts here, but then it is unlimited going in that direction. And every one of those cells contains that blank. Okay. And so that's the tape symbols. Tape symbols, of course, involve all input symbols, involve a blank, and you can throw in anything else you want, as you will see. And then we have a move function. I will talk about that in a minute. And then we have an initial state. Q0 is an element of Q. It's the initial state. And finally we have F, which is a subset of Q, the set of final states.
Professor, could you go over what that first line says? It says Q is a finite set of solutions or states?
States.
Okay, states.
So that is essentially a Turing machine. And if you look at Q, T, you suitably restrict the move function, and you have Q0 and F, then that is basically your finite automaton. This is this. Okay? And so now the move function we have to explain a little bit better, because as I said in the informal discussion, you take a state and a tape symbol. So your read-write head is looking at a cell that contains a tape symbol. Initially, of course, presumably it will be an input symbol, unless your input happens to be epsilon, which is certainly possible, in which case it will look at the blank, because that's what would indicate that your input is epsilon. And so, but in general, you have a state, which is part of the finite automaton, and you have a tape symbol, which is T0, and you're going to map that into, well, you change that to another state, and you change it to a tape symbol. Usually, if you want to be nitpicking, you're going to take that blank out. Most of us would probably not come up with the idea of changing a tape symbol, a non-blank tape symbol, to blank. So, but anyway, some books write it T0 minus blank, some books just ignore that minus blank. You can play it however you want. It doesn't make much difference. And then we have left or right, which basically says to the read-write head, go to the left or go to the right. And so if you go with the finite automaton, then basically you're looking at this. Well, ignore the subscript 0. In finite automaton, of course, this would just be t. And it would go to a state. And so you can immediately infer from that the Turing machines that we're defining in some sense are deterministic, because we're going to a single state and we're going to change that tape symbol to some other tape symbol, and we're then going to move left or right. So if you ignore the moving left or right and you ignore the rewriting, then the red stuff that we have here is basically a finite automaton, more specifically a deterministic finite automaton. We're not really going to consider non-deterministic Turing machines. One can do that. They're not really any more powerful, and they're just a greater pain in the neck. So we're going to ignore that idea, but of course one can define non-deterministic Turing machines. We're not doing that, and in as much as Turing machines are already the most powerful thing that one can define to do something, as we defined them, non-deterministic, a deterministic, not non-deterministic one. So throwing in non-determinism isn't going to do you any good. It's not going to make it more powerful. Okay, so that is the idea, well, that's the formal definition of a Turing machine. And then the way it functions is, as I said, you have the initial configuration where the input is at the beginning part of that tape, and then the input is followed by blanks, and the read-write head is looking at the first tape cell that is there. So as I said, this is semi-infinite. It starts here and then it goes all the way as far as you want to go to the right. And so that then is where things start in the initial state Q0, with the read-write head looking at the first tape cell. And then you consult your your move function to determine what you're going to do. You are in a state. Initially, that would be the state Q0. You have something in that first cell, a tape symbol, and then that will then tell you to move to some other state and rewrite the content of that cell, and then move to the left or to the right. Obviously, in the initial situation, it probably isn't a particularly good idea to move to the left, because that means you fall off the tape and you die an instantaneous death. So in that case, obviously, that's not going to be helpful. In this case, of course, the word would be rejected, but that's probably not what you want to do. Although, I mean, it is possible that if you have uh, mm, if you want to accept A union B star, so meaning a word that starts with an A and then has any number of A's or B's, well, if you see a B in the first cell, then one way of saying to hell with you, I am not going to accept this word because it starts with a B, is to then make a move to the left, falling off the tape, and that would then obviously reject that word that starts with a B. But that usually things are a little bit more complicated than that. So, any questions about this before I'm going to show you an example?
I have a couple of questions. One of them being like, could you give us a little bit more context in terms of what the Turing machine is doing in terms of like
Well, you will see that in the example.
Okay, so because my main question is more like before Turing machine, it seemed like we were able to answer most of the questions possible, right? So we were able to, except for whenever we deal with a certain context.
Oh, you have the same situation with Turing machines. Just hold on.
Okay.
The example will illustrate that. I can define it in the abstract, but it probably doesn't do you much good. If I show you an example, it will be much clearer.
Okay, I'll hold off. Thanks.
Sure.
What do the dollar signs mean next to W1?
Oh, in this case, this is just a separation sign, W1, and then if you want a semicolon or whatever. So in this case, dollar sign is not in the words. So that means that basically you take the first word and then you say it's dollar sign, which means that was the end of the first word. Then you do the second word and then you say dollar sign, that means this is the end of the second word, and so on and so forth. Okay?
Thank you.
All right, so let's look at this example. A to the n, B to the n, C to the n greater or equal to 1. We've already seen that this language is not context-free, so we know we can't find a push-down automaton or a context-free grammar for that matter that would allow us to deal with this language. The automaton would accept, push-down automaton would accept, the grammar would generate this language. So how do we define a Turing machine? Well, obviously we need an initial state. And now what we're going to do is we have obviously A and B and C. These are our input symbols. So T is A, B, C. And then what we're going to have is a capital A, a capital B, and a capital C, and a blank. So T0 is T, as well as capital A, capital B, capital C, and blank. And so the idea here is, well, let's just look at A, B, B, C, C. A, B, B, C, C. So this is 6 cells, and then there's a blank. Yeah, obviously, everything after that is blanks. And so what we're going to do is initially the Turing machine is in state Q0, initial state, and it will look at the first input symbol, which is that first little a. And so what we're going to do is we're going to change that little a to a capital A. Okay. And having changed that, we move to the right. And how far do we move to the right? Well, we bypass a little a until we get to the first little b. Now that first little b is going to be replaced by capital B. And then we keep on going. So bypassing b's, little b's, until we hit the first C, which again, little c is going to be changed to capital C. And at that point, so far we've moved from left to right. So this is always move right. And then we turn around. And how far do we go? Well, in this case, we bypass capital C's, little b's, capital B's, little a's, until we get the first capital A. So this is now going right to left, which is, of course, there and there and there. And so there is our first capital A. And at this point, we turn around again. And we see, well, what do we see? We see a little a. And that little a then is going to be changed again to capital A. So now we get a second sweep from left to right, where just as in the first sweep, we found a little a and its corresponding little b and its corresponding little c. And so now we're going to do the same thing again. Second sweep, this is now our little a, which we're going to change to little b, capital A. Come on. And then we bypass capital B's because we're not really interested in capital B's. We're interested in little b's, so that capital B is no good. But the little b is interesting because that is now going to be changed to a capital B. And then we go on bypassing capital C until we get to a little c, which we're going to change to capital C. And then we have to turn around again because, oops, no, not red. Turn around and go back until we hit the first capital A. And then we turn around. And what we see now is a capital B. There are only two possibilities after we hit that first capital A in that right to left sweep, and that is another little a, which was the situation here, or a capital B. Everything else is no good. And so if we have that capital A followed by a capital B, then we have to make sure that there are not going to be any other little b's and no other little c's until we get to the blank, and at that point we accept. So how do we do that formally? Well, we are in state Q0. We change that capital A, I'm sorry, that little a to a capital A. So if we look at this, we change to a state, we write down what we change that content, and then we move to the right or to the left. So in the first case, we go to state Q1. We change that little a to capital A, and we move to the right. And if we see anything else, then that is no good. We don't want to see a little b, we don't want to see a little c. I want to see a capital A, capital B, capital C, nor a blank, because n is greater or equal to 1. So there has to be at least one A and one B and one C. So that starts the whole process. So we have Q1, and in Q1 now we are going to troll for a little b. Okay, so that means we bypass little a's. So this is Q1, right, little a. We bypass capital B's because these are already things that we have messed with. And what we're looking for is a little b, because that is the little b that would correspond to the little a. And so at that point, we change that to a state Q2. We change the little b to capital B, and we still move to the right. We don't want to see a C. We don't want to see a capital A. And we don't want to see a capital C, and we don't want to see a blank. So in state Q2, we are not interested in seeing a little a, because we basically just changed the little b to capital B. And so what we're looking for is a little c. This is what we're really going to troll for, the little c. We don't want to see a capital A. We don't want to see a capital B, and we certainly don't want to see a capital C or a blank. But we have to bypass capital B's. Why? Because there could be... No, nonsense. That's not what it is. We don't want to see a little b. Oh, no, I'm sorry. This is correct. Getting confused. We go Q2, little b, and right. So we basically bypass all the little b's after we've changed the one b to capital B. And so now we're trolling for C, little c's. So this is Q3, capital C, and, well, I will fill that in a minute. So getting a little cramped. And the one thing that I had a slash which was wrong is I need to bypass this capital C's. So Q2 capital C and right, because basically, that's the situation. So you have a bunch of A's followed by a bunch of B's followed by a bunch of C's. And so you change the first little a to a capital A, you find a corresponding little b, change that to a capital B, find a corresponding little c, change that to a capital C, and then go back. And so you go back until you hit the first capital A, and then you move to its immediate right. And if that happens to be a little a, you're going to change that to a little a, and then you look for the first little b, which means you may have to bypass a's here, little a's, and you may have to bypass capital B's until you get the first little b, which you then change to a capital B, and then you bypass little b's and bypass capital C's until you get the first little c, which you change to capital C, and then you turn around. So that means once we have seen, so we bypassed the little b's, which we did, and we bypassed the capital C's, which we did, until we find the first little c, and that little c then is going to be changed to a capital C, and then in state Q3 we turn around, which means we now move to the left. So in Q3, what are we looking at? In Q3, we're looking for the first capital A. Okay? Because the first capital A is what we need when we go towards the beginning of the tape. And so at that point, well, in Q3, what do we have to bypass? Well, we certainly may have to bypass little a's. Q3, little a, left. We may have to bypass little b's. Q3, little b, left. We have no business seeing a little c. We have to bypass capital B's, Q3, capital B, left. We have to bypass C's, capital C's, Q3, C, left. And we obviously don't want to see a blank. And so that is basically that sweep from right to left, where we're trolling for a capital A, because that basically is the last little a moving right to left, is the last little a that we change to a capital A. And so that then is where we're going to change to state, well, which state? So at that point, we want to go to a state, let's leave that open, and we change the A, we keep the A, and then we move to the right. And what do we want? Well, we want to see whether this is state Q4. In state Q4, then we have to inspect what it is that we have to the right of that A we trolled for. So this capital A that we trolled for in the right to left move, that then in Q4 will tell us, well, what are the two possibilities? Either what we look at in Q4 is a little a. Okay? Or what other possibility is there? It could be a capital B. So these are the two possibilities that in Q4 are possible, because essentially we've had the first sweep from right to left, and then a sweep back from left to right, and having encountered that capital A, we now are in state Q4, and in state Q4 we look to the right of where we found that capital A in that right to left sweep. And at that point, there could be, as I said, two possibilities. There could be another a, little a, in which case we just do whatever we did before. Okay, so that would then be Q1, a and right. Little a and right. And Q2, b and right, if we see a little b. We don't want to see a little c. We certainly don't want to see a little a, capital A. But we may see a capital B, which means there are no more little a's. We've had all a's matched with all little a's matched with little b's with little c's. So now we've exhausted all the little a's. And so what we're going to see to the right of that last little a that was changed to capital A, we see now a capital B, which means at that point we have to go to state Q5, and we keep that little capital B and we move to the right. And we don't want to see a capital C, and we don't want to see a blank. So what happens in Q5? Well, in Q5, we basically now, to the left of the first capital A that we get first moving right to left is a capital B, which is what we have in this case. Q4, we read capital B. So that's the case. We keep that capital B and go to state Q5. And then we bypass all B's. We don't want to obviously see any little a's. We don't want to see any little b's. We don't want to see any little c's. We don't want to see any capital A's. We will bypass capital C's. And we do that until we find a blank. QF, whatever, blank, and left. And QF is accept. So that is the Turing machine for this language. It basically has 1, 2, 3, 4, 5, 6, 7 states. It is deterministic. It is not particularly efficient. You basically, if you have a word of length 3n, you're basically going to move order of n squared times, because basically you go all the way until you see the first little c. That's n, 2n and then you move back, that's another 2n, then you move 2n again and back, and so for every a, so this is n times 2n, so it's about 2n squared moves altogether. So this is not particularly efficient, but it will do the trick. And it does it in a fairly straightforward way. It should be fairly obvious that if you wanted to do something like a to the n, b to the n, c to the n, d to the n, e to the n, the overall idea is the same. You simply you replace the little a's by capital A's, little b's by capital B's, little c's by capital C's, little d's by capital D's, and little e's by capital E's, using exactly the same trick, sweeping left to right to draw for matching letters and changing them and then going back and so on and so forth. So the ABC is not going to be significantly simpler than ABCDE, for instance. It's more, but you just have those sweeps involve not just 3 symbols, little a changed to little b changed to little c, and little c changed to little d. Of course, all of that has to be done with a change in state, but in this case, you would then change little d to capital D, and then another state change little e to capital E, and then you sweep backward. So once you understand this process for a to the n, b to the n, c to the n, then you can clearly generalize that so that you don't have any more complications. I mean, the general idea is really exactly the same. Any questions?
I have a question.
Yes?
Under lowercase b in Q4, since we're not looking for a lowercase b, shouldn't we know? Because we're only looking for a lowercase a and a capital B.
No, Q4 is basically doing the same, similar things as Q1. The only difference is, of course, see in Q4, how do we get to Q4? Q4 is basically the sweep from right to left, trolling for right to left the first capital A. So there we find it, and then we go to Q4, and we're bypassing in Q4. Sorry, this. See, we're tying it back to Q2 here. This is Q1. This is Q2. So the idea here is when you are in Q4, okay, theoretically, you could have ask me again what you were concerned about.
So in Q4, we're looking for a capital B or a lowercase a.
No, we're not looking for a capital B.
Since we just read a capital A?
let's see. In Q4, we are basically going back. So we're looking for A. So in Q4, we found that A, the first A. And so now we go to the right, which could be a little a. Okay, I see what, basically, we don't really need that. There can't be a little b. Because in Q4, we found that capital A from right to left, moving backwards, if you will, unless you're right, your language from left to right, Arabic, for instance, in which case it is the right direction, but for us Westerners, it's the backwards. So from right to left, that's sort of going backwards. And so in Q4, we found in the backward sweep the capital A. And so there are two possibilities. If what is to the right of that capital A is another little a, then we go back to Q1, where we troll for a little b. It can't be a little b, so that's why I removed that. It wouldn't make much difference. It would still work, but economically you don't really need that, so let's get rid of it. This, on the other hand, says in Q4, the capital A, which is the last little a that was changed to a capital A, is the first capital A that we encounter in that backward sweep. And so what to the right of that capital A could be, it could be a little a, which case we did I screw up here? I did. We don't want to do it that way. Let's see. With all the explanations I'm giving you, I'm screwing things up. So we have a little a. That little a is supposed to be changed to a capital A. I'm sorry. So that goes to Q1. And then in Q1, we're basically trolling for the first little b. Okay, and so, all right. So please change that. Q4, and if we see a little a in Q4, which is of course what we see to the right of the last capital A, or the first capital A on the backward sweep, which is of course the last capital A that we got by changing a little a to a capital A. So if we have a little a to the right of that capital A, then we want to change that to capital A and then troll for a little b. If, on the other hand, what is to the right of that capital A is a capital B, then we should be done. So did I confuse now everybody? Basically, in Q0, we just start the process. Okay? We change the first little a to capital A. And then in Q1, we bypass little a's and troll for a little b. That, of course, eventually will also require us to bypass capital B's, because you may have several capital B's before you get the first little b. So you have this and then that and then that. And so in the little b that gets changed to capital B, that is then transitioning over to state Q2. In state Q2, we throw for a little c, which we then change to a capital C. In state Q3, we basically move to the left, bypassing what we have to bypass, which is little a's, little b's, capital B's and capital C's, until we hit the first capital A. And so there, this is the lift move, backwards, if you will. And then in Q4, which is where we hit that first capital A on the backward sweep, if we have a little a to the right of that capital A, then we change it to that little a to capital A and go to Q1. And there we throw for little b again. Same thing. On the other hand, if that capital A has to its immediate right a capital B, then that means we now have no more little a's, which means we shouldn't have any little b's, and we shouldn't have any little c's, which means when in Q5 we bypass things, we should not have a little a, we should not have a little b, we should not have a little c, we should not have a capital A because we turned around once we saw the capital A, the first capital A in the right to left sweep. And so we should see capital B's, we should see capital C's, and then eventually we should hit the blank. And in that case, we accept. Sorry, so Q4 needs to be fixed. Everybody clear now?
Well, Professor, I have a question about the blank slashes, not the blank symbol, but the slashes.
Right.
So if we have an input string, are we supposed to know based on the input string that certain moves are not possible, and therefore we put the blank area in the table?
Right. I mean, if you're in Q0 and your read write head is looking at the first cell, this language, A to the N, B to the N, C to the N greater or equal to 1, any word in that language has to have at least one little a. And so in Q0, we start things off by moving under that little a to state Q1 and change that little a to capital A. If we had a little b, that would be fatal, because that would mean the word starts with little b, which is no good. Same thing for C, same thing for capital A, capital B, capital C, or blank, because n is greater or equal to 1. Now, if n were greater or equal to 0, then in Q0 we would, so let me do that green, if that were 0, then we would simply have to add QF, blank, right. Okay, so if it were greater or equal to 0, then the empty string would be included, which means in Q0 in the initial state, we might have a blank in the first cell, which is fine because that means that n is 0, so A to the 0, B to the 0, C to the 0, this is epsilon, and that would then be accepted. But for what I have, n greater or equal to 1, not the blue but the black, you wouldn't have that. So when you have that slash, the slash basically says no good. And that means the word is, of course, rejected. Does that clarify? Okay. Any other questions?
I see that in Q5 you also skipped over C. Is that because it follows a language where A, B, and C all are all the same length?
Okay, what happens? Okay, we're going, say we have this is the last capital A, which, so we'll have A, little, 3 A's, 3 B's, 3 C's. So at this point, when we go back, we change that little c to capital C, then we draw for a capital A. And at that point, we look to the right of that capital A, and it turns out to be a capital B. So this is that situation. That's where we change to Q5. We keep that capital B, move to the right. There could be several more B's. That's why we have to bypass them. And then we get to the capital C's. That's why we have to bypass them. And finally, we're going to get to the blank here, and that is this. Does that clarify it?
Yes, thank you.
Okay. Any other questions?
So Professor, we're gonna have the exam next Wednesday, and after that, what lectures will be left and what content will be covered after that?
We will talk about the halting problem of Turing machines. We will talk about undecidability. We will talk about all kinds of fun stuff.
So will those topics be included in the final exam, but not on exam 3?
Of course. I mean, I'm obviously covering it after exam 3, but there will be questions, at least one question on that stuff in the final.
Okay. Yeah, I was wondering, like, when was a good time to ask you about question 3 on the exam 2? If you could, like, work it out, because I missed it and a lot of people missed it mostly.
Question 3?
Yes, with the complementation and...
Oh, I don't quite understand. I mean, we went through all that extensively. I mean, this is much easier than the Turing machines.
Yeah.
You mean that?
I don't know. I never got it.
This one?
Yeah, if that was the one.
Yeah, I mean, so A star so A star would be this accepting and this accepting and this rejecting, and complement would be this accepting and the other two rejecting, and B star complement would be this B, B, A. I'm doing it faster. I don't expect you to do it that fast, but I'm just showing you. So this is B star complement. And then you do the concatenation, sorry. So let me 0, 1, 2, 0, 3, 4, 0, 1, 2. I'm sorry. What was the alphabet was ABC. Then we have to throw in this C, C, C. And so from 0 under A we go to 1, and B and C go to 2. From 1 under A we go to 1, 2, and 2. And 2 goes to 2, 2, 2. Sorry, there's a C missing here. And so this is 0, 0, 1. And then we have 0, 3, 4. A, B, C. And 0 goes into B to 3, 3. And everything else is 4, 4, 4, 4, 4, 4, 4, 4, 0, 0, 1. So these are the two automata for A star complement, B star complement. Then you do the concatenation. This is rejecting, so you copy. This is rejecting, so you copy. This is accepting, so you take this with that. So this is 2, 4, 2, 3, 2, 4. And everything else is copy, 4, 3, 4. And then you have the only state that is accepting is 4. So you have that, and then you have to make that deterministic, and that'll give you an automaton, A, B, C. And then you have final states, and then you flip those, and that'll give you then deterministic finite automaton for the complement. All of which is kind of straightforward, isn't it? What's the problem here?
I think that whenever I encountered this one, the original problem that I felt was the actual complementing part. That on its own was a little bit of a doozy, but I mean, once explained, I feel like it's understandable.
Okay. Any other questions? Anybody wants to take pictures of slides?
Yes, please.
Slide 1. Slide 2. Slide 3. Slide 4. And slide 5. Okay. So I will talk to you on Monday. Have a good weekend. Bye-bye.
Bye.
Thank you.